Hi. Let's take a look at Lamkin number 1. Again, I'm just picking these proofs out because I know how tough they can be. And again, you've got the answers there, but sometimes the answers don't always help. I know there's times where you question some of the steps. So let's take a look at this one. Prove that if two chords are congruent, then they are equidistant from the center of the circle. All right, so I've got the circle O drawn. I've got two chords A, B, and C, D, which are congruent. I'm going to mark them as such. And then we're trying to show that they are the same distance from the center of the circle. Before we start that, let's just kind of do a quick recap. How do you decide, or how do you define the distance from a point to a line? I think that went all the way back to chapter 4. Let me just make sure, because I feel like I had marked that page off specifically for this discussion. Yes, there it is. Back on page 1, no, it wasn't 167. It was in the Your Turn to Play. No, in the, sorry. Should have had this right to the page before I started this video. But it was in one of the problems in the cities at the end of chapter 5, I believe, where it talked about the foot of the perpendicular. Yeah, problem number 1 in Cambridge, which in my textbook is on page 181. So it just talks about how you find the distance between a point and a line. And what they said was you're going to drop a perp from the point to the line. So when we go to find the distance between the point O and AB, we're going to drop a perp right here. And we're going to drop a perp right here. And those two segments will be called the distance between the point O and chord AB and point O and chord CD. All right. So let's go ahead and do the proof. So if we do that, we're going to say the first thing we know, and this goes back to a proof that we did in Valdez, problem number 1. Remember, we did problems 1, 2, and 5. So this was problem 1. And it says that the angle bisector of any chord must pass through, I'm sorry, not the angle bisector, the perpendicular bisector of any chord must pass through the center of the circle right here. So if we drop this as the perpendicular, that also is going to be the bisector right there, and same thing, that would be the bisector right there. Or we should say, I guess, the angle, I don't know why I keep saying angle, the segment chord bisector that is perpendicular will pass through the center of the circle. So let me just write that. The perpendicular bisectors of AB and CD pass through O. Right, and again, switching pencils here, that came from the theorem in Valdez number 1. Right, that through that the perpendicular bisector of a chord passes through the center of the circle. Right, so then number 3 is going to say, well then, let's call this, I think he calls them E and F, yeah. Just trying to be consistent so that if you wrote this down and you want to check some steps, you'll have the same lettering. So then AF is equal to FB, and CE is equal to ED, and that's just the definition of bisect. And I believe Sarah has brought this up in class. Does bisector deal with congruence or equality? And I looked into that and shared the response one day in class, I think, and it seems to go either way, that sometimes the definition talks about the bisector cutting it into two equal segments. Sometimes it talks about doing two congruent segments. Really, it could be either one. So we're just going to use the equal part of that there. Okay, number 4 says that AB equals CD. We could have put that right up here. I'm not sure why I didn't do that, but the AB and CD are equal to each other. That is part of what that says right there, that they are congruent. So this is definition of congruent segments. Again, you could have put that way up there at the beginning. All right, step number 5 says that we are going to say that AF plus FB equals AB and CE plus ED equals CD. This is a long, long time since we've seen that reason. And that comes from definition of between. All right, again, if we have two segments that they add together to equal the entire segment, only if that point that's cutting them right there is on the line segment, so that we called that definition of between. All right, number 6 says AF has to equal CE. And he gives a reason of algebra there. That is a lot of algebra that he's just skipped in that point. So let's kind of off to the side here talk about what that would be. So we've got AF plus FB equals AB. And we've got CE plus ED equals CD. So let me work with this one right here. I know that AF and FB are equal to each other. So I'm going to replace FB with AF. And I'm going to work up here just so I don't bang into this one down here. I'm going to replace FB with AF. So I get AF plus AF equals AB. And then I'm going to say 2AF equals AB. I'm going to do the same thing down here. I'm going to say I know that CE and ED are equal to each other, so CE plus CE equals CD, or 2 CEs are equal to CD. I also know that CD and AB are equal to each other. That was from step 4. So I'm going to say 2 AFs are equal to 2 CEs. And then I can just cancel out this 2, and I get AF equals CE. So there's a bunch of algebra involved in that, but that's what he would do. That's what he did in order to do that. All right, step 7 says that then segment AF is congruent to segment CE. Reason, definition of congruent segments. Number 8. I'm going to insert a step here that he doesn't, because again, he's not always consistent with this. Draw OA and OC. All right, sometimes he does it, sometimes he doesn't, so I'm just going to do it. So it is 2 points to determine a line. Number 9 says that OA is congruent to OC. Again, some of these should start to seem really familiar because we've used them quite a few times in our proofs on circles. And this is all radii are congruent. All right, number 10. So again, if I draw them in there, OA and OC, those are congruent. Right there, drawing them in my picture. OA and OC are congruent. I also know that this is perpendicular here, just that's the definition. I also just found out that AF and CE are congruent. All right, we haven't really been marking them on there, but that's what we've got. So hopefully at this point, as you're looking at it now, you see, oh gosh, I've got 2 right triangles. I've got the hypotenuse of one congruent to the hypotenuse of the other. I've got the leg of one congruent to the corresponding leg in the other. Those 2 triangles now are congruent. All right. So then we can say here as step 10 that triangle AOF is congruent to triangle COE. All right, and our reason is HL. Let me scooch this back a little bit because I'm bumping into stuff on Abby's desk. Now that those two triangles are congruent, we can say that this extra side that we didn't know about, this extra leg, OE and OF, those also have to be congruent. So OE is congruent to OF, reason CPCTC. Right. I would probably just stop there. Well, actually, no, that's not true. The last step would be OE equals OF, and that is definition of congruent segments. I wouldn't stop there because what he asked us to prove is that they are equidistant from the center, and distance is a number, not a segment. So instead of stopping here at just saying that they're congruent, we're converting it to numbers. The length of OE is equal to the length of OF, and this is the distance from O to segment or chord CD, and this is the distance from O to chord AB. And so we're showing that the distances are equal. Okay, that's the end of that proof. Thanks.